expert, well, I would say, both in quantum field theory and in statistical mechanics. I have been working on at the interface between those two subjects for many, many years. So I am, I hope, equally incompetent in both subjects. And I am teaching here the second part of the quantum field theory course, which we have three purposes, I think. It will deepen and present in a new way things you have seen already in the first part of the quantum field theory course. So first, I am planning to introduce something you have already seen a little bit in Ben Schumacher course, which is the path integral quantization. So first, I am planning to cover path and functional integral quantization. Functional will be just a generalization of the idea of Feynman about how to quantize a quantum field, mechanical systems by means of sum over paths or classical histories to field, to relativistic field. Therefore, one has to integrate over functions, fields, rather than just trajectories of a particle. So that's why it's called functional integral formulation. So the second part of the course, so this will be basically, I hope, the first week. The second part of the course will be to discuss one of the very, very important and deep aspects of quantum field theory, which is renormalization, something which is not present in ordinary non-relativistic quantum mechanics, but which is one of the most important features of quantum field theory. It's the need of renormalizing the theory, both to deal with technical problems related to the appearance of infinities in perturbative calculation, but it's also related, in fact, to some of the deepest aspects of quantum field theory, which is that the concept itself of what is a coupling constant, what is a field, depends on the scale at which you look at the phenomena. You know, in quantum theory, everything is about what you observe and in which state the system is, and the concept itself of what is unobservable, of what you measure, depends on the scale at which you measure it. And that's one of the deepest aspects of quantum field theory, of the quantum world. So renormalization and renormalization group, because in fact there is a concept of a group of transformation associated to the change of scales at which you study the system, are very important. So this will be, I hope, the second week. And the third part of the course will be to discuss, by the means of functional integral method, something you started to study in the first part of the lecture by Constantin Zarembo, which is a quantization of gauge theory. So I think from the note he sent me, I haven't checked exactly, but you have mostly discussed some aspect of quantization of abelian gauge theory, QED. And therefore, I will discuss both abelian gauge theory and quantum electrodynamics from the point of view of functional integral method. But I will start to discuss a little bit what's, of course, most important for modern physics, which is non-abelian, so abelian and non-abelian gauge theory. Okay. So this is and some aspects of so I will discuss in all these three parts. I will remain at a quite abstract and mathematical level. I will not try to do a lot of physics out of that. In particular, for the application of non-abelian gauge theory, I think you will have to wait the course by Michael Peskin to really learn some physics and what is useful. But it will be, I hope my lecture will be a prerequisite for what he will be doing, which is an interesting thing. Okay, so perhaps just one last word about before starting discussing the content of the lecture. First, the format of the lecture are quite short, so you have to absorb a lot of things in a small time. So I won't have time to discuss many mathematical details. So I will try to remain at to give you a broad view of what's going on in the field. But it's very important to try to redo the calculation I've just been sketching to present, because to really understand what quantum physics is, you have to do the calculation. You have to understand how it works. From the physical point of view, quantum theory is still a bit mysterious to many of us, including me. And it's really, you really have to play with it to appreciate how beautiful and how consistent it is. Otherwise, some things can stay mysterious, and you can keep discussing about the meaning of what is a measurement in quantum theory, what is entanglement, what is causality. And if you can discuss a lot, and it's only when you do actual calculation that you realize that quantum mechanics work as it really does. Okay. So the second thing I wanted to do, which is a general feature about quantum field theory. So quantum field theory 2 is the title of the lecture, is that quantum field theory is not only interesting because it's the real theory, the real physical theory which describes our universe, our world, but also if you really want to understand what is quantum mechanics, you really have to discuss the issue of causality, of measurement, in the framework of theories which have an infinite number of degrees of freedom and which are relativistically invariant. And that's why it's very important to understand what a quantum field theory is, even if after that you are going to ordinary, physics, condensed matter or astrophysics, or where you don't really need any of the subtle aspects of the relativistic world we live in. You still have to remember that in the back of your mind, the real world is relativistic, because it has to be causally. You have to meld together causality and the structure of space-time, which enforce the fact that the universe is relativistic. Okay, so that's the end of those general consideration, and let us start to discuss path integral quantization and functional integration. Okay, so I understand from what I have been looking at the web last week that with Ben Schumacher you have been introduced a little bit into what is path integral quantization, Feynman sum over histories. So I will assume that you have already some knowledge of it. So if I explain something that I consider that you know it and you don't know it, don't hesitate. Just raise your hand and say, "Hey, help! We don't know that." Okay. So and today I will mostly discuss path integral quantization and present some reminds you of something. Fix my notation and the language I will use, and discuss that. And I will go to quantum field theory during the next lectures. Okay? So let me remind. As far as I know, so what you have been you have seen in the quantum mechanics lecture that if you start from just a very simple system, a quantum system which is one particle, mass m, living in one dimension, so it's living on a line, and it's non-relativistic. Okay, so that's, and it's just the only force it can feel is a force which derives from a potential. So there is an external potential, Okay? And therefore, what you have to consider is that to describe the state of your particle, here is the position, Q. This is the position of the particle. The position is somewhere here. And it feels a potential V of Q. And therefore, the Hamiltonian, so in classical mechanics, the system is described, for instance, by an action, S, which means that to any trajectory, here I plot the time, here I plot the position of the particle, and the particle in time, if you start from some time, let us say t1, and you end up at a time t2, its classical motion is described by a trajectory, a classical trajectory that I call Q of t. Q of t. And Q denotes just the data, the corresponding trajectory. And the action is just the integral over time of, well, let us denote the time S, to denote that it's the time between the two particles, of the sum of its kinetic energy, m over 2 q dot squared, minus the potential energy, V of Q. Okay, that's the classical action. And you have to extremize this action. I will come back later. So if you consider the variation of the action, if you make a variation of the trajectory, the classical trajectory are the trajectory which extremize this action. So delta S equals 0 of Q equals 0 means classical trajectory. Okay. And in the following, I will mostly consider a very simple system, which is the case where the potential is just quadratic, so it's we can call it that way. M is the mass of the particle. There is a frequency omega naught, and Q squared, because this is the case of the harmonic oscillator, the well-known case. Oscillator. Okay? So, this system, now, this is for the classical description of the system, the quantum mechanics. We know very well that it's described now. If you go to the quantum, the system is described by an Hamiltonian, H. The Hamiltonian is now an operator, and it's the sum of the p squared over 2m, where p is the impulsion, plus m over 2 omega naught q squared. This is the Hamiltonian. And then what you have seen is that if you consider something which is called the evolution operator, or the propagator, which is that it is just it's an operator which tells you how the states of the systems, of the particle, how the wave function are transformed under time evolution, and it's simply exponential of t over I h bar the Hamiltonian. So this is the evolution operator. And the evolution operator is such that if you start from a state psi naught at time 0, then under time evolution, psi t is given by u of t applied to the initial state psi naught. So it's just the solution of the Schrödinger equation. And if now you consider matrix elements matrix elements of this evolution operator. You have seen in the lecture of quantum mechanics that this object that I can describe, I think it was called K, but I will call it Q. So I will consider something which is, I explained already what are my choice of notation. This is simply you consider a system which starts from a state where it's located at a position Q1 at time 1. So it's just the wave function is located at position Q1. So it's an eigenstate. Q1 is an eigenstate of the position operator. And you consider that at the end, you project the system on the eigenstate of the position operator Q2. So the particle starts from point Q1 at time T1. You want it to end up at Q2 at time T2. And you want to estimate the probability amplitudes for this process to occur. And this is given, of course, by this matrix element. So it is a matrix element of the evolution operator between time T1 and time T2, sandwiched between the initial state Q1 and the final state Q2. Okay? And this is the description of this object in Schrödinger picture. Okay? But you have seen in quantum mechanics, I think, that there is also another way to describe the evolution of the system, which is a Heisenberg picture. And in the Heisenberg picture, this will correspond to starting from a state where the position is at position Q1 at time T1. You end up with a state where the particle is at position Q2 at time T2, and you just measure the products, the scalar product between this state and this state in the Heisenberg picture. Okay, so those are two different ways to write the same object and to write the same matrix element. Okay, and what Richard Feynman told us is that this can be written as a sum over all passes times a phase, which is exponential I over h bar times the classical action associated to this particle. So you have to sum over all trajectories, where, of course, the trajectory starts from Q1 at time T1 and end up at time T2 in Q2. So this is the famous path integral formulation of Feynman. Okay, so this is the classical action. Classical action. Not for a classical trajectory, but for any trajectory you can imagine for the particle. And this is a measure on the space of histories, if you want, or path. Okay. And a lot is contained in fact, a lot in the physics, in the exact definitions, is contained in the definition of the measure. So I hope you have seen that this measure is defined, in fact, by cutting the trajectory into small pieces of time and discretizing the system, assuming that particle propagates like that, and then taking the limit when the interval of time goes to 0, and that's a precise way to define this sum and what the measure is. So I won't discuss that more at that time, but it's very important to keep that in time. Okay? Okay. Okay, so that's what you have seen. And now I want to start to do something very a bit strange. So let us do it here. I would like to use this blackboard, but I don't know you here. Can you see if I write here? Yes? Okay. I presume after that it's not working, so we'll do that here. Okay? So, what I will be doing is I will ask something stupid. I will ask what happens when you consider that this operator, u of t, considered as an operator, what are its properties when time is not a real variable, but you consider it as a complex variable? So u is just the exponential of the Hamiltonian times t divided by EIH. And let us consider that we are in a system which is like the harmonic oscillator. So the potential is something like that. Okay, this is Q. And the spectrum of the system is something like that. So the spectrum is bounded from below. The spectrum of the systems, EI, I equals 0, etc., is bounded from below. And in fact, you know that for a quantum system to make sense, it must have a lowest energy state, which is a vacuum. So the spectrum of a quantum system, in fact, is always bounded from below. Okay? And then u of t, of course, is just given by this formula. Is if you use a basis of eigenstates, so you consider that you have the eigenstates I, such that h of I equal EI I. This is the basis of eigenstate. This is an operator which is diagonal in this eigenstate with the eigenvalues exponential t divided by E h bar h. Okay? And it's easy to see from that that this operator, in fact, is what mathematicians call a bounded operator, which is a bounded operator means an operator such that all eigenvalues, there is a bound on the on the norm of the eigenstate of this operator, and it's a bounded operator provided that the imaginary part of the time considered is negative, is non-positive. Okay, because the eigenvalues of this system are just exponential t divided by E h bar times the energies, and as long as time has a small negative imaginary part, this is the exponential of a phase times a norm which is exponential of a negative real number, so it's lower than 1. Okay? So if you consider an object such that this object, let me derive it in this way. Here is this is a real physical time. And in the formula, let us assume that time can have a small imaginary part, and I call tau equal it, for instance. So when tau is positive, it means that t is imaginary with a negative imaginary part. In fact, this object, considered as an operator acting on the space of states, on the Hilbert space of the states of the particle, is an object which is well defined in this domain. Okay, so you can do sensible mathematics with the evolution operator, with the propagator of your quantum theory, as long as time lies in the lower half plane or its boundary, which is the line of real physical time. Okay, so as a mathematical object, it's perfectly licit to consider this object. Okay, and let us consider in particular what's happening if t is entirely imaginary, so it's minus I times something tau, where tau is positive. Okay, so we are somewhere here. Yes?
Me. just a mathematical trick?
At the moment, it's just a mathematical trick. But we'll try to do some physics out of it, which will be important. Okay? So, for the moment, I'm just doing a mathematical trick. I'm continuing in complex time what we are able to do in real time. But one remark. Theoretical physicists and mathematicians have some strange mind, and that always, when they have something, they always try to complexify it. To say what's happening if it's imaginary. It happens for time, it happens for position, it happens for angular momentum, for instance, in quantum mechanics. A lot of things can be, a very interesting thing can be done in quantum mechanics by considering that the angular momentum of the particle is complex, and even the dimension of space is often considered as something complex, non-integral. So it's a very useful mathematical trick. Okay, so if I do that, then what is this object? Let me call it UE of tau. So it's just a redefinition. It's U of minus I tau. So this object I call UE of tau, and this is an operator, and it's simply exponential of minus tau times the Hamiltonian. Okay? So it's another operator. Well, this operator is a unitary operator because it's an evolution. So this is not a unitary operator if tau is real, but it's a self-adjoint operator. Okay? So its eigenvalues are real, while here its eigenvalues are complex and lies on the unit circle. Okay? And what is important with this analytic continuation of the evolution operator for real time to imaginary time is that this is something you know, in fact, very well in quantum mechanics, because it's a part of the density matrix of the same systems at finite temperature. You know that if you consider now the same system, so same system, here an harmonic oscillator, in equilibrium, with thermostat or bath at finite temperature T, you know that these quantum systems cannot be described, cannot be considered as being in a pure state. It has to be considered, it is, you have to consider it as being in a mixed state, a probabilistic mixture of pure states, and it's described by a density matrix. So another operator acting on the space of states, which is called rho. And to the temperature, I associate this Boltzmann factor beta, which is 1 over Boltzmann constant times the temperature. And this density matrix, which I call rho beta, is just 1 over some normalization factor times precisely this exponential of minus tau h, with simply the relation that tau is 1 over h bar times beta. Oh, no, there is an h bar. I'm sorry. So it's tau over h bar. I'm sorry. It's, of course, minus tau over h bar h. I forgot the h bar. Okay. And what is z? Z is simply the trace of u O of tau, and it's called the partition function. So it's a number. It's called the partition function of this system. Okay? So it's a trace of this Hermitian operator acting on the states of the system. Okay? And if you know the density matrix, in fact, you can reconstruct all what are the expectation value of all observable of the system in this mixed state. So all the physics of the system is described by the density matrix. Okay? So now the question is, what becomes this formula if instead of considering the evolution operator at real time, I consider this operator? So what happens if instead of considering a real time, I consider the evolution operator at an imaginary time? So, okay, and then I will just give you the results because it's an easy exercise. Okay. So the question now is there a way to represent by a sum over histories of the systems this object, which is now what I will call UE of Q2 tau 2 Q1 tau 1, which is exactly the same thing. It's simply the matrix element of this operator, where in this case we have seen that this object is well defined if tau 2 is larger than tau 1. So this tau 2 minus tau 1 has to be positive. Okay? So you see that in order to do that, you just have to make this transformation. Consider that you start from the formula where the time is real, and now you make it imaginary. Okay? So one way to derive a path integral formulation for this object is just to take boldly the formula for the path integral in real time and to make this transformation. Okay? So if you do that, what do you get? Yes?
There is a derivative with respect to time. How,
yes. No, not in H, in the classical action. In H there are operators only.
Oh, I see. Okay.
Yes? So the question is, what happens to this object? Okay? So, then, if you do this transformation, now what you have to consider is that you have to make a sum over trajectories, histories, Q of sigma, where now sigma is equal to minus IS. So remember, in this formula. So you take this formula and you write the action. Okay? And what becomes the action if you make a transformation like that? If you replace Q of T by Q of sigma, where sigma is an imaginary time. So the action becomes S of Q, which was integral over T1 to T2 of ds m over 2 dq over ds squared minus, well, let us call this V of Q. What does this become? I made a transformation, so first I have the factor I, which comes from this factor. So I get an I times integral from tau 1 tau 2 d sigma. Okay? Now the minus V of Q doesn't change, because I'm just making a change of variables in Q. But now there is also a change of sign, because here I have a derivative of Q with respect to S, and the derivative of Q with respect to S becomes I times the derivative of q with respect to sigma squared. So I get the m over 2. Okay. So if I make this transformation, it's some kind of black magic. I get something minus I integral over d sigma m over 2 dq over d sigma squared plus v of q. Okay? So let us call this a new action SE of q. So SE of q is just this. So the difference between the classical action here and this new action, SE of q, is that this SE of q is now given by the sum over the kinetic energy, if you want, is these new variables of time, plus the potential. So it's something like an energy and not an action, not a Lagrangian, but in this variable. Okay? And once you have done this transformation, you can do the same thing here, and you realize, in fact, that this object is simply given by a sum over now, a sum over all the paths, depending now on this new variable sigma. So I must have that q of tau 1 equal q1 and q of tau 2 equal q2. And then I have an exponential of minus, because here I had an I over h bar. Here I have a minus I over h bar. And therefore I got, no, this is sigma is plus. So there is a minus here. So there is a plus, I'm sorry, something very important. And here is a 1 over I. I made the usual, when there is 1 sense to make a sign error, I got it wrong at all time. Okay, so this is the formula. Sigma is plus I times S, because when the real time is minus I times something, this is positive. Okay, and therefore there is an I factor here, there is an I factor here, so I get a minus 1 over h bar times SE of q. Okay? So you see that you get, and in fact there is also a little bit, there is an I factor which changes in the measure, but so you get for this matrix element of basically the density matrix, you get also a path integral formulation, but now this is a path integral formulation. But there is an important difference now. So now you have something. Now what you have to consider is that here is the position of the particle. Here is your imaginary time, if you want. Imaginary time. You have to consider, as usual, passes which start from Q1 and which end up in Q2. You have to sum over all possible trajectories, but the weight associated to each trajectory now is a real weight. It's not a phase like that. It's a real weight, and it's something which is smaller than 1, because it's the sum of the kinetic energy plus V of Q. And so you see that a trajectory which fluctuates a lot like that, if you compare it to a trajectory whose fluctuations are small, this becomes much larger. Okay? Because the instantaneous speed of the particle along this trajectory is much larger. So this term is much larger. The kinetic energy is much larger. So the weight is much smaller. because the exponential of minus 1 over h bar SE of Q. So such a trajectory is very, has a very small contribution in this integral, while such a trajectory has a much bigger contribution. You see? So, if you have used this formula, okay, this means that you can construct the matrix element of this evolution operator at imaginary time as a probabilistic sum over histories. So this is a real, what mathematicians called a probability distribution. So if you are doing quantum mechanics at imaginary time or considering the properties of a quantum system at thermal equilibrium, in fact, you can use the Feynman integral formulation, but you are in the realm of probability theory, so which is something which is much more easy and well known by mathematicians. So this is probability distribution. Okay. Okay, so that's the first thing which is important. In some sense, yes?
So when do we care about this and when do we care about the other one?
Yes. This one, you mean?
Yeah, the original
Yes.
one. When do we care about which? Like, I guess I'm not entirely clear on why we want both.
Okay.
When we want
First, I will use that many times during my lecture because it's easier to consider mathematically. Okay?
But it describes a different physical thing. Mainly something at thermal equilibrium.
Physically, it's very different. But if you know how to compute things at imaginary time, and see if you get some explicit expression, for instance, for some matrix element of some operators, and you get an explicit expression of this imaginary time, then you take the formula and you turn to real time again, and you instantly get the result.
So it's a different, we could calculate something there and then transform back.
Yes.
So it's like doing Fourier transform to like
Yeah, so one advantage of this form of considering this object is it's often more easy to calculate,
Okay.
especially for mathematicians, because mathematicians like very much, and they are right, probability distribution. There are a lot of theorem convergence. This is an integral which is an integral of a trajectory. So it's still an awkward integral over an infinite dimensional space, but it's an integral with a weight which is positive and which is decaying if the trajectory are too wide. So it's something the mathematician knows a lot about. While this one, it's something which is much more difficult to construct mathematically. Yes?
To do this analytic continuation, do we have to assume anything else about the Hamiltonian apart from being bounded?
Basically, no, in fact. Well, I won't go into the mathematics. The mathematics are very deep. But basically what you have to assume is that you are working in a space of bounded operators. And well, if you really want to understand this from a deep mathematical point of view, you have to enter into the theory of operator algebras and of von Neumann and von Neumann operator algebra. It's a very deep and difficult mathematical theory, and there are theorems which tells you what are the conditions for this to be possible. But basically, in fact, there is a very deep theorem I don't have time to describe, which states under which condition to any density matrix object like that here, you can associate the time evolution. So there is some deep mathematical structures behind that, between this analogy between density matrix, namely a probability distribution on the state of quantum states, and the fact that you can associate Newton and Hamiltonian and the time evolution. Okay? But that's far beyond the purpose of this course. So, okay, so what should I do? Okay, so you see that you have this formulation. You can rewrite the matrix element of this operator like in terms of this path integral, where now the action is something real, which is the sum of the kinetic energy and the potential energy. And you have 1 over h bar here. Okay? So, now first, I should explain why I call this S with an E, a capital E, and why I call this U E. Okay, so why the E in this denomination? The E is for Euclid, the well-known Greek mathematician. And Euclid has, of course, nothing to do with quantum mechanics. But the fact is that, in fact, when I am think about doing this transformation in a general space. Now, let us go back for a little bit from quantum mechanics to real Minkowski space. So I'm now back in a relativistic universe. And you know that in a relativistic universe, you have time, you have space, and the element of space-time is given by something like, of course, I will not use the notation of Konstantin Zarembo, but I will assume that the signature of space-time is minus plus plus with C equal 1. So this is a space-time element in my notation. So the signature I use is minus plus plus plus. This is the signature of space-time. I too choose. It's just a definition. I choose this definition. Okay? This is a definition you can find, for instance, in the book by Steve Weinberg, but it's, of course, not the definition which is in Michael Peskin's books, for instance. Okay. Well, okay, so now this is ordinary Minkowski space-time. Space-time. Okay. Now make this transformation. Consider that instead of having time, you assume that time in minus I tau. What does becomes the space? Now you have tau x with dA squared equal d tau squared plus dx squared. Okay? So you see now that if you do this operation, time has become just one ordinary component of space. So this is the ordinary metric in Euclidean R4 space. Okay. Okay, so that's why this time is usually denoted Euclidean time. SE is called an Euclidean action. Etc. In fact, the kind of things I've been doing is just that I've been doing by this operation, rotating Minkowski space-time into Euclidean space-time. Okay? And so the ordinary Feynman path integral becomes, by this operation, some probability distribution over histories in Euclidean time with the Euclidean action. Okay, so that's the first reason I use this denomination. Okay, so the second reason is that you see that this weight looks like a Boltzmann weight. You see, this weight, this exponential of minus 1 over h bar SE of Q is similar to something like exponential minus 1 over so effective temperature times some effective energy. Or let us forget about K star. It has the same form that exponential of minus 1 over some temperature times some energy. Okay? So you see that this quantum systems, in fact, quantum system at finite temperature is mathematically, by this formulation, it's analogous to a classical one-dimensional system, which is described by Q of 2. So you have some dimension, and you have some system describes but what is the position of the particle at the position tau. So, okay. And the energy of this configuration, of a configuration, is just this SE of Q. And what is the temperature of this classical system? The temperature is nothing but h bar. Okay? Mathematically, in this, it's just a way to rewrite the temperature in this classical system. In this term, if you consider this as a partition function for a classical system, what is the temperature here is the Planck's constant in the original system. So this means that the quantum fluctuation in the original systems are similar to the thermal, if you want, the thermal fluctuation in these systems. So you have a mathematical mapping. It's not a physical mapping. It's not that this physical system is the same than this physical system, but you have an equivalence between the problem of a single particle, a single quantum particle at finite temperature, with some kind of a chain of a one-dimensional system. You can view this as a chain of oscillators, for instance, a one-dimensional chain of oscillators at finite temperature. But what is the temperature of this one-dimensional system is the Planck constant of this zero-dimensional system. Zero-dimensional because there is only one particle. There is 1 degree of freedom. Here you have 1 degree of freedom. Degrees of freedom. And here you have an infinite number of classical degrees of freedom, which are the Q of sigma here, or the Q of tau. Okay? So there is a deep boundary here, but there is a mapping between what you compute in a quantum system and what you compute in a classical statistical system. And that's also very useful. Yes?
In SE, the different terms correspond to different aspects of this one-dimensional system.
Yes, in fact, I can do a tutorial about, or half a tutorial about that. If you want to consider what is exactly the classical system continent with that, it's really, you can view this system as a chain of oscillators, of copper oscillators. And perhaps I will, but it's better if I show you a picture, so I can do that at the beginning of the next lecture. This will be a chain of coupled oscillator. This corresponds to the energy of each single oscillator, and this is a coupling between neighboring oscillator, because this describes how the energy depends on the difference in the position of Q with this position on space. But I will come back later. Okay. So, one last thing.
Sorry, how can we say that the quantum system we started with is at finite temperature?
Pardon?
The system we started with is at finite temperature.
I come to that. I come to that. Because, for instance, I would say that because this system has a temperature, and what becomes the temperature of the quantum system in this description. And I come back to that immediately because I can keep this on. And let us now consider what is a partition function. It's a partition function. See. The partition function is a trace of this evolution operator. And we know how to represent, here in the Schrödinger picture, the matrix element of this operator UP. Okay. What is a trace? A trace of an operator is just the sum over the eigenstates of the basis. So it can be written, for instance, as the sum over the eigenstates of the system n of exponential minus tau over h bar, the energy of the systems. That's the standard, the usual definition of what is the partition function of a system. But you can also rewrite it in the basis, in the position, in the basis of position states. Right? So you can rewrite it as an integral from minus infinity to plus infinity over the position of a system here. Okay, of, I'm sorry. Yeah. This one. Of Q T minus tau over H Q. Well, this is what I call it. So, tau is the difference between and this, I have a representation. I have this path integral formulation in Euclidean time. And here the only constraint is that I'm considering paths which start from a point, end up at the same point, and then I sum over all possible initial and final configurations. So, this is simply, in fact, a path integral over all possible path in Euclidean time, dE of Q, the same H bar SE of Q, same probability weight associated with each trajectory. But now the constraint is simply that Q of 0 equal Q of tau, since I am considering first that Q1 equals Q2 and then summing over all possible Q1. So this is simply a sum over periodic trajectories in Euclidean time with this relation. Okay? See? So, you can view that by simply make once again the same picture. Here I have my Euclidean time sigma, here I have the position, and this is the initial time is 0, this is tau. Tau is related to the temperature of the bath to which your quantum particle is coupled. Okay, so T is the temperature. And you are summing over all possible trajectories. Simply you are imposing that trajectory ends up at the same point for any trajectory. So you are able to consider this trajectory, okay, or any trajectory like that, they simply have to be periodic in time. Okay? And so, if you think about it as a classical system extended in this direction, you simply have a classical system with periodic boundary conditions. So in fact, the last element of this dictionary between quantum and quantum theory and classical statistical mechanics is that the temperature here, the temperature of the quantum system is not the temperature of the classical system, because the temperature of the classical system is a Planck constant. It is the size, well, it's in fact, it's given by this formula. Tau is the size of the system. The size of the system, because you have an extended system, simply it's closed. So it's like a ring. You have a ring, you are considering a ring, like that, which has some length. And the temperature is simply the length or the size of the systems to the power -1. So this is the last element of the dictionary. The higher the temperature of the quantum systems, the smaller your ring is. And the lowest the temperature of the system is, the larger, the longest the system is. Okay? So you have to keep in mind this very important dictionary. Quantum system at finite temperature equal a classical extended one-dimensional systems. The energy of the configuration of these classical systems is the Euclidean action associated to the quantum system. The temperature of the classical extended system is Planck's constant. So the thermal fluctuations are related in some mathematical way to the quantum fluctuations of the quantum systems. And the temperature, and if you want, the size of the classical extended systems is the inverse of the temperature of the classical system. Okay? Yes?
The temperature of the quantum system as show up.
Where?
Do we ever, I mean, where in our equations is the temperature of the quantum system?
It appears here because T is the inverse of beta, and beta is proportional to h bar. So the density matrix, remember, is 1 over z. It's 1 over z times exponential of minus beta h. So the temperature occurs in the density matrix. And I still have, we started a bit late, so may I have still 10 minutes?
Yeah.
Okay. So then I will show you exactly one of those kind of games you can, one of the kind of things you can compute using this kind of trick. Okay? So, let us assume that you want to compute, for instance, you want to compute the expectation value of some observable. Let us call it A, and it will be a function of the operator Q. Let us consider that we consider something which is, for instance, it can be Q, it can be Q squared, it can be cosine of the position of the particles in a thermal state. in a thermal state. Okay? So I want to compute what I will denote A of Q beta in the quantum system of the quantum system, of the original quantum system. Okay? And this is, of course, we know that this is trace of rho beta times A of Q. Okay? That's the definition of, well, from the principle of quantum mechanics and the properties of the density matrix, as it has been defined by von Neumann and Landau in the end of the 20s. This is the expectation value of an observable A measured on the systems where you only know that this system is at a temperature T. Okay? And so this is, what is this? This is trace of exponential of U E of tau times A of Q divided by trace of UE of tau. Okay? So this, we know what it is. We have computed it. This is a partition function. We know that it is given by the sum over D of Q exponential minus 1 over H bar S E of Q over periodic path. Okay? Now, can we compute this object by path integral methods? You have seen in the quantum mechanics lectures that the expectation value of some observables times the evolution operator can be also computed by path integral method, and it's something very simple. This is simply the same integral over dq with the same weight associated to each trajectory. Simply, you multiply by the function A of Q of, let us say, sigma equals 0. Okay? So this means that this subject is simply given by the same sum over trajectories. Simply, you weight it by what is the value. So this is the value of A of Q at Euclidean time sigma equal, let us say, 0, because you are considering something which is time invariant. Okay? So you see that this is simply this quantum expectation value of a quantum observable is simply the ratio of the sum over all trajectories of A of Q of sigma equals 0 divided by the partition function. So this is simply nothing else. That's a classical expectation value of A of Q of 0. It's an expectation value, in the statistical mechanics sense. You see? So quantum expectation value of some observables corresponds to the standard expectation value in the statistical mechanics system. Is it clear? Okay. And therefore, in quantum physics, and especially in high energy physics, one is interested, in fact, usually not into expectation value of observables over a thermal state of the systems, but into expectation value of observables in the vacuum state of the systems. Usually, one is interested into the vacuum state. Let us call it omega or 0 of the system. Okay? And if I do that, how could I compute the expectation value over the vacuum state of the systems? Well, that's very easy for this system, from this formulation. You see that to a state of energy En is associated a probability exponential minus tau over h bar En. So, if you are interested into what is the expectation value of the observable A of Q over the vacuum states, what you have to take is the general expectation value of this quantum observable over the thermal states and take the limit when beta goes to infinity, because this corresponds to the limit where the temperature goes to 0. And when the temperature goes to 0, all these exponentials becomes very, very small, but for the one for the lowest energy state. You see? And therefore, the expectation value of a quantum observable in the vacuum or in the lowest energy state of the system is simply obtained by taking this ratio of these two observables. So this is given by the expectation value of A of Q for in the limit where the size of the one-dimensional statistical system goes to infinity. You see? Because you always have this relation, beta equal 1 over t, so t goes to 0 means beta goes to infinity, but beta is proportional to the size of the systems, so the periodicity of these physical systems. Okay? So, projecting on the vacuum, if you want, is equivalent to take what is called the thermodynamic limit for this statistical system. Okay? Sorry. So, consider a system, and when it becomes very infinitely large, and you just remember that at infinity there are periodic boundary conditions, then you have projected onto the vacuum of the quantum system. Okay? Okay, so I think I should end up there. I will just mention one last result, which is something very important, but I will have to come to that later. That I think you have seen in the lectures in quantum mechanics that, in fact, one is interested for many, many purposes, not into the expectation value of some single observable, but one is interested into the expectation value in the vacuum state, let us call it omega, of the time-ordered product of operators. Okay? In quantum mechanics, what is a time-ordered product? It's simply, for instance, the products of two-position operator of your harmonic oscillator at two different times. So this is the time-ordered product. time order product. And these are two different times. Okay, but everything works exactly the same for that. What you have to do to compute the expectation value of a time-ordered product of two position operators for the harmonic oscillator in the vacuum of the energy oscillator, what you have to do according to the rule I gave you is that. Okay. Here I draw again my picture with here real time and here Euclidean time. What you have to do is to remember that in principle you have a period here proportional to the inverse of the temperature. What you have to do is that you have to perform your path integral over Euclidean time in this direction, okay, with periodic boundary condition here. You have to compute the expectation value of the product of Q at time tau 1 and Q at time tau 2. So you have to compute something which will be the expectation value of Q of tau 1, Q of tau 2 in the Euclidean theory. And then, once you have this formula, which is a function of T1 and tau 2, you go back to real time by making this transformation that T1 equal I tau 1, T2 equal I tau 2 in the formula. Then you get here T1. Here you get tau 2, and by making this transformation, here you get some mathematical formula. You make this transformation, and you get precisely the expectation value of the time-ordered product of Q of tau 1, Q of tau 2, over a thermal state beta, with beta is proportional, let us forget about the factor h bar and kBt, to this. So if I compute in the Euclidean theory the expectation value of this object by summing over those periodic boundary conditions, I get something, I compute something, then I make back this change of variables which correspond to going back on the real timeline, starting from something I computed for imaginary time, and I get this object, which is expectation value of some time-ordered products of operator, average over a thermal state. And then I take the limit beta goes to infinity, or t goes to 0, and I got what I wanted, which is this object. So the vacuum expectation value. Okay, and next, I think, in next lecture or the next one, or during some tutorials, we shall compute that explicitly and check that this coincides with the calculation of you get in by doing canonical quantization. Okay, so thank you. Yes.
It's known as a Wick rotation.
Yes, it's called, I wanted to describe that later tomorrow. It's called the Wick rotation. That's the name by the French. Well, not the French, but the physicist. I don't know if it was English or
Italian.
It was Italian. Oh, yes.
Question. So if instead of, say, computing the expectation value of Q T1, Q T2,
yes.
I compute the expectation value of Qt2 and Qt1,
Yes.
where the time ordering is the same. When we rotate back, what do we get?
If you, I'm sorry, I misunderstood.
Yeah, instead of computing the expectation value of Qt1 and Qt down there in the Euclidean theory,
Yes.
yeah. If I compute the opposite, like Qt2 and Qt1,
Okay, I can.
is this because the it's periodic? That it doesn't. That
No. Okay, I think I will need some. I can reply just now, but I think I will need some more time to find the detail. Here, I'm computing something which is just the expectation value of this object, and here I've replaced. So when I compute this, you see, I just compute something which is an integral of q exponential minus 1 over h bar s q times q of t1, q of tau1, q of tau2. So the order, the fact that tau1 is larger than tau2 or tau2 is larger than tau1 does not matter at all, because I'm computing an integral. Okay? Now, the question is that here, for instance, I am in a case where tau1 is smaller than tau2. Just, okay, tau, this is tau to 0, tau positive. So tau1 is less than tau2. If I make this rotation, I have to change by the same I, the 2. So t1 is less than t2. So what, and in the path integral formulation in real time, first I'm computing q1, then the system evolves, then I'm applying the operator q of t1 times q1, then the system evolves, because this is the order type, and then I apply t2. So then what I'm computing in the order type is q of, first q of t1, this is the initial state. Then I apply q of t1, then the system evolves, and then I apply q of t2. Okay? And then I have summation. So here this doesn't mind. If I go back to real time and I want to think about it in terms of something I'm computing in a quantum theory, since time flows in that direction, the evolution operator is u of this t. First, I am applying qt of t1 on my state. Then I am applying q of t2. So this is the time order product of q of t1 of q of t2. And if t2 would have been before t1, t2 would have been before t1, and therefore what I would have done is that if tau2 is less than tau1, then this would mean that t2 is less than t1, and then I would have measured the expectation value of this, the product of those two operators. Now this is t2, so first I apply q of t2 on my states, then I let the system evolve, and then I apply q of t1. So therefore, depending on whether tau1 is less than tau2 or tau2 is less than t1, I obtain this product of operator or this product of operator. And this is by definition, the time order product of those two operators. But that's a bit sketchy. I will explain that more in detail in the case of quantum field theory. This really makes sense. Okay? Yes?
Path integral is better defined in the Euclidean picture, is that right?
Yes.
So we should really be thinking everything in terms of the Euclidean thing first,
Yeah,
and then
it's often something which happens. So that's what I want to do. And also it will be important to consider that path integral formulation works as well in Euclidean time than in real time when dealing with issues of renormalization theory. Because then it's much better to see, from my point of view. that's not that's my art point of view. I feel more at ease in Euclidean time than in real time. Any more questions from the present? If there are only questions by the tutors. But, yes?
Why did you put A of Q sigma equals 0? Why are you considering A of Q and sigma equals 0?
That's simply because this is an observable. In principle, you can measure an observable at any time. But a thermal state is a state at equilibrium, so it's invariant under time. So you can compute the expectation of some operator depending on time. In a thermal state, you will obtain the same results, the same number, at any time. So in fact, it means that if you are considering a single, here I have been considering two operators. If I am considering a single operator, forget about this one. And if I am measuring this expectation value of this object to measure the expectation value of Q of T1, then it's not important if I measure it here, because the action is invariant under time translation, and I am summing over periodic path. So I know that I can do that, and if I go at the extremity, there is nothing special about this point. So this point is the same with this point. So I can move and move and move. So I can choose to measure, in fact, as far as I'm interested, if I am measuring the expectation value of a single operator local in time, I can choose it to measure it at time equals 0, the origin of time. It will be simpler. That's just a convenient choice. Okay? Yes?
Are there any conditions under which you're not free to rotate back into the real time?
No, the only condition is that if you go further and try to go that. So, but otherwise, as long as you have the initial assumption that the evolution operator is well defined with the rule lower half plane, you can do whatever you want. You see, simply here I have taken this path in time and I moved it here. And that I am allowed because any intermediate state like that consists in doing that. And as long as the time path go down in this direction, that's allowed. What you are not allowed is to do something like that. If you have to do, for some reason, when you compute your things, if you have to do something like that, then that's very bad, because you know that the evolution operator in this time direction is not mathematically well defined. So you will have a lot of unpleasant infinities popping out in your calculation. So this is forbidden. But as long as you can claim while your deformation path in time, if you want to play, goes in this direction and or is at most horizontal, then you are fine.